Hi. So today I want to do a quick video on the concept of impulse response and convolution because they go hand in hand with each other. So let's discuss what we mean when we find the impulse response of a system. And from a mechanical engineering perspective, I like to give the example of a mass attached to a spring, where the mass has a mass of m and the spring has a spring constant k. And imagine that I take some giant hammer. Here's my hammer. And I'm going to swing it to hit the mass. And it's going to make a very sudden impact with the mass, kind of like a clap with a lot of force. And we will say that that effect that hammer has on the mass, we call that an impulse. So an impulse is force acting over a small amount of time. That's what it is in general, the idea of something being hit and it causing motion to happen. And if you were to ever plot force versus time, and I were to give you some force that just happens at some point, some sudden force, where you have some value, F, that occurs over delta t, we say that the impulse, whatever that physical property is, that is given by F delta t, which is, if we look at this as a rectangle, F is the height and delta t is the width. That is the area under the curve. And we say that this is our impulse. We call that F hat. This here is the impulse. So we can quantify an impulse based on the force that occurred and over what time period it occurred over. But from a system perspective, we want to look at one very specific impulse. So this is introductory, what we just did, just to show like some clap or a hammer or something happening. I kick something and it's going to move or vibrate. And on its own, sure, I can learn to see how the mass displaces due to that arbitrary impulse. But what's unique is if we use the specific impulse equal to 1, we can actually learn a lot about our system. So if we apply an impulse of 1, we can ultimately determine what our system does for any input force. Because think about it like this. If I were to give you this system here, I have that experiment in my lab, and I'm interested what that thing is going to do for a cosine input or an exponential input or a logarithmic input or something really random, some random force that is acting on that mass. This is arbitrary. If I know what the system does in the case when that force provides an impulse of 1, I could then use that to determine what the output is for any arbitrary force. Now, the specific thing that causes an impulse of 1 is what's called the Dirac-Delta function. Dirac-Delta causes an impulse of 1. By definition, this is something we need to know. Dirac-Delta is given by delta of t. If I were to apply, let me just arrow around, I drew it backwards from our usual notation. If I applied delta of t, this is the same. This is basically equivalent to f hat equals 1. Well, I'll just say it's the same as when f hat is equal to 1. Delta t produces that impulse equal to 1. And that is the specific impulse we care about for our long-term goal of determining any output of the system due to any input force that's arbitrary. So let's say I give you a system, and I'm going to give a system that if you're in MechLab 2 with me, this is a homework problem where I say, let's say I give you a system where the mass is 2 and the spring constant is 8. And if you remember from our free body diagram in this situation, we would end up with our system parameters on one side and the input force on the other side. And I have all of the useful characteristics of the spring mass system filled in here. And this is the equation for any arbitrary force. Oops. That's what it is for any arbitrary force. So what we want to do is first understand how our system responds to an impulse of 1. So how does the system behave due to an impulse of 1? That is what we call, whatever that output is due to that impulse, we call that the impulse response function. And we use the letters h of t to indicate that. And for this idea of a spring mass system, we typically care about what the mass is, position is as a function of time. That's usually what I care about. So this h of t is the same as x of t, but for the very specific situation where the force is equal to what, do you think? Because the impulse response is the response due to an impulse of 1. When does that impulse of 1 occur? Due to what force? Well, that's what I wrote up here. The Dirac-Delta function is what causes an impulse of 1. This is basically our input. And from a vibrations perspective, this would have units of newtons. It is a force that is causing our mass to move. So this is the same exact thing. The impulse response is the position of the mass or the output of the system when the input force is specifically the Dirac-Delta function. If that does not make sense, I want you to rewind this video and watch that section again, because that is so crucial to understand. The impulse response is a property of the system. I have some system. If I hit it with an impulse, it will respond in some way. And that impulse, from a mathematical perspective, is caused by the Dirac-Delta function. So, if I were to say find h of t for that same question I just wrote, that's what you're given. If we want to find the impulse response, we have to replace this force with the Dirac-Delta function. That is the force, specifically when we are looking for the impulse response function. Because again, delta of t produces that impulse of exactly 1, and that's what we are interested in. That is our baseline. Now, to go ahead and do this, we could take the Laplace transform of both sides. So let's say we do the Laplace of both sides of the equation. And in the problem, I tell you that all initial conditions are 0. So that means our Laplace transforms get a little bit easier. If we look at our table, we'll see that the Laplace transform of the second derivative, the constant stays. This Laplace transform of the second is 2s squared x of s plus 8 x of s. And the Laplace transform of delta of t, by definition, ends up being 1. That is the Laplace transform of the Dirac-Delta function. So I would like to solve for x of x, so I can factor that out. And then ultimately divide by the 2s squared plus 8. This is x of s, which is the Laplace transform of our output x of t, which is, for this specific force, the Laplace transform of the impulse response function, h of t. They're one and the same when the input is delta of t. So what we want to do now is find x of t using the inverse Laplace transform to get out of the frequency domain. And this is where a table of Laplace transforms becomes useful. Because if you look at a table of Laplace transforms, the one that this most looks like is something like omega over s squared plus omega squared. And what we would like is to take our x of s and rearrange it so that it looks like that, because the inverse Laplace of this ends up being sine of omega t. So if we have the correct form, right now we don't because of a few things. One, there's a 2 in front of the s squared. That needs to be re-represented somehow. And depending on what omega is, we need another omega in the numerator. So we have to do all that manipulation to ensure that we match the table. Once we do that, we take the inverse to give a sine of omega t. So let's figure out what to do. Well, first off, I want to make sure there's no 2, this guy, in front of the s squared. So I'm going to factor it out. And you might be thinking, well, there's still a 2 there. But since we factored it out and now it's being multiplied by things, if we were to take the inverse Laplace transform, which is some sort of integral, that 2 can basically come out of the integral. Before it couldn't, because it was next to the s squared exactly. But now that we factored it out, that 1/2, 1 over 2, can be removed from the integral and left there as a constant. So another way to think of this is that this is the same as 1/2 times 1 over s squared plus 4. We are closer now. So looking at this, if this is going to match this, what does that mean omega is? That means that omega has to be 2. Because this would be 1/2 1 over s squared plus 2 squared. Which is beginning to look a lot like the form that we have up here. What is the final thing that's missing? We need an omega up here in order to take the inverse Laplace and get signed. So since omega in this example is 2, I need a 2 at the top. So for more manipulation, I'll just multiply by 2 over 2, which is the same as multiplying by 1. We're not changing anything. We're just re-expressing it, which will give us this 2, and the bottom 2 will give us ultimately 1/4. And now we have an expression that matches exactly this guy. Omega over s squared plus omega squared, 2 over s squared plus 2 squared. They match. Which means if I were to say that x of t is the inverse Laplace of x of s, which is the inverse Laplace of 1/4 times 2 over s squared plus 4, this 1/4 can come out of the inverse Laplace because it's a constant. And now we're taking the inverse Laplace of this thing, which matches that. So that means the inverse Laplace of that function is sine of omega t, where omega is 2. So that tells us that x of t, this must be 1/4 sine of 2t. So this is basically the output of the mass due to that impulse, which is why this is the same thing as h of t, because this is the specific function. This is the output when the input is the Dirac-Delta function. That is the definition of the impulse response function. When the force is delta of t, we are looking at how the mass or how the system responds to that specific impulse. So this is our answer to part A. We're asking to find the impulse response. The reason that the impulse response is so useful is that we can use h of t to find the output for any input. So if I had that same system and I apply a force that is the natural log of t times the square root of t or some random stuff like that, I don't know what that means. But we have some weird motor or something that's causing this thing to move back and forth at this weird way with the natural log and the square root of t in it. We can use the impulse response and that force to find the output. And the way that we use them is via convolution. This gives us the output for any input. And without going through the details of the proof, the equation says that the output is going to be the integral from 0 to t of our input, which in this case is a force. And I'm going to use a dummy variable tau. f of tau times the impulse response of t minus tau, t tau. And essentially what we're doing is summing up the different displacements for different combinations of impulses and step responses. So in general, if I were to give you some arbitrary force, and the force look like that. If I were to look at one section of this, we see that this is basically an impulse at that exact period of time. And we know that when the impulse is 1, x of t is equal to 1 times h of t. I'll just write it like that for a second. If I were to increase the impulse, because it's one for specifically the Dirac delta, but I might have other impulses at play depending on the force. I can generalize and say that my x of t is the same as some impulse times the impulse response function. It'll be some multiple. So when I hit it with an impulse of 1, it does something. If I hit it with an impulse of 2, it'll do the same exact thing, but it doubled the amplitude. So this equation here, because if we remember our definition of f hat, this was f delta t. If you look at convolution, f delta t is kind of secretly hidden. This is f, that is like a delta t, but we're looking at very, very small intervals of time, at differential time dt. And we are multiplying that by the impulse response function, except depending on the point in time we're at, we are shifting it. So here's a new impulse at a different point in time, a different tau, but now we are looking at the impulse response because it's been shifted by some amount, tau. Remember, if we include in our argument here, p minus tau, that means we are shifting by some amount, tau. And by integrating all of these f hats times h of t, you're determining the total output as a function of time. That is the general idea behind convolution. So a nice thing about convolution is, I'm just going to copy and paste that equation I just wrote, is that if your bounds are from 0 to t, convolution ends up being commutative, in that instead of doing f of tau, I could do f of t minus tau, h of tau, d tau. And those are equivalent. And this will give us the output for any f. Remember, f is arbitrary. But once I have h, the impulse response, I can do this operation to get the output for any of those input f's. Really powerful. So for the example where we just found, what was h of t? 1/4 sine of 2t. We just said that h of t was 1/4 sine of 2t. I told you in this problem that the input is a step. That is 12. And I want to know what the output of the system is due to that input step of 12. So we can do this with convolution, where we'll say that the output, and in this case, the output is the displacement, is the integral from 0 to t. And maybe we'll do this first one, where we see f of tau. What does that mean? Well, we have f of t here. And that's saying if I plug in t, I will always get 12. So if t is 1, it's 12. If t is 2, it's 12. It doesn't matter what t is. So if I were to do f of tau, that's saying plug in tau into that expression. And since this expression is independent of any variables, that means that this is just simply just 12, which is really convenient for us. I don't need to change anything. Now, we have to do the same type of thing, except now we're going to do it for the impulse response, which was this guy. And here's the t. So right now, if I plug in t, I get 1/4 sine of 2t. If I'm going to plug in t minus tau, this will be written as 1/4 sine of 2. Instead of t, we're plugging in t minus tau. I'll plug in t minus tau, and then ultimately integrate that with respect to tau. I hope that we see that. So if we were to do this integral, the 12 and the 1/4 can come out. That's a 3. The integral from 0 to t. Sine of 2t minus 2 tau d tau. And keep in mind what our integration variable is. Our integration variable is tau. It is not t. T is a constant. So let's say we just do u substitution. I'll just do this to be very thorough. I'll say that u is the inside of this. Oops. I'll keep the taus there to remind us what our integration variable is. It's going to be sine of u. And now we need to find what d tau is. So if I were to do du with respect to tau, that 2t goes away. We just get -2. Which means that if I were to solve for d tau, I would get -1/2 du. I'm hoping that that's not too hard from the calculus 1 perspective. So this will be multiplied by -1/2 du. That -1/2 will come out with the 3. And then we will integrate from tau of sine of u du. That is the same as the integral of sine is negative cosine of u from tau equals 0 to tau equals t. And I'll plug the u back in so I can use my tau values, my tau bounds. U was originally 2t minus 2 tau. Tau is equal to 0 to tau is equal to t. So if we do that, we will have to plug in, maybe just for simplicity, these two minus signs will just become positive. I'll get 3/2 cosine. Remember, t stays. T is not the integration variable. We're plugging in for tau. 2t minus 2t, because this is where we're plugging in t for tau, minus cosine of 2t minus 0, because in that situation, we're now plugging in 0 for tau. So if we do that, we get 3/2 cosine of 0 minus cosine of 2t. This is the same as 1.5, 1 minus cosine of 2t. This is the specific output when the force is that step of 12 in this specific example. I use the impulse response, which is a property of the system, to determine what that output is. And if I gave you a different output, it's the same procedure. The h of t is the same, given our mass is 2 and our k is 8. That doesn't change for that system. But if I change the force, I'll change the output. I can find that output by convolving the force with the impulse response. Now, that was kind of annoying because of the U sub. Sometimes we can be smart. And let's say we go ahead and use this other definition. You'll see what I mean when I say we can be smart. So I'm going to copy and paste a few things. Let's copy and paste this. This is x of t. And I'm going to copy and paste our h of t and our f of t. So in this case, I'm now going to be shifting f, which based on my colors, it's this guy. So if I plug in t minus tau to 12, there's no variable. It's still 12. There's no variable to replace. This is still 12 times. Now we just do h of tau, which is easier to plug into the impulse response as opposed to t minus tau. That got a little bit annoying because we had to do u sub. Let me change the colors a bit. This is 12 times 1/4 sine of 2 tau d tau. And again, this is what we're plugging in. So if we take out the 12 and the quarter, we get the integral of sine of 2 tau d tau. So at this point, what we can do is integrate sine of 2 tau, which would give us a factor of 2 when we do u sub that we need to replace with a half. And that'll give us negative cosine of 2 tau integrated from 0 to t. This will be negative 3/2 cosine of 2t minus cosine of 0. Once you plug in your bounds, it's going to be negative 3/2 cosine of 2t minus 1. If we were to multiply by the negative sign, we would get 1.5, 1 minus cosine of 2t, which if we zoom back to our original answer, that is the same thing that we got here. 1.5 times 1 minus cosine of 2t is the same answer we get no matter the order we do. It's a nice property of convolution, not only to make it easier, depending on your force or your impulse response, but also to check your work if you did it both ways, because you know they have to match. So again, to summarize, the idea is if you find the impulse response of the system, which is the specific impulse or the specific output when the input is the Dirac-Delta function that causes an impulse of 1, we can use that h of t with convolution to find the output to any input force. Very powerful, because if I know ahead of time what my system is going to be exposed to, I can design for how it's going to behave. I hope that makes sense. If you have questions, please let me know. Otherwise, I'll talk to you soon. Thank you. Bye.